So, good afternoon. Thank you very much for inviting me here. And I'm sure you are rather tired at this point, so I am going to entertain you with a little bit of quantum physics in order to understand a little bit of foundations of what Professor Janssen was talking about, because we have a big overlap in our presentation. So I will focus more on foundations, and then essentially at the end of my talk, I will briefly discuss quantum cryptography. So, it's 100 years of physics, quantum physics, you know. So we have the International Year of Quantum Science and Technology, and this is the reason why I'm here today. So I will start essentially where the whole story begins. It is in 1878, a very young physicist came to talk to most prominent physicists of his time, Philippe von Joly. A young physicist was Max Planck. And Max Planck was asking Philippe von Joly, does it make sense to study physics? And the response was, no, it is not. Everything is essentially solved. It's like Lord Kelvin, the same type of view. The physics is solid. There are a few bits and pieces to fix, but otherwise we are done. Nevertheless, young Max Planck stayed in physics. And essentially, 20 years later on, he was studying a very practical problem. The problem was about calibration of thermometers. For the industry, it was very important as then. Today is very important. And one of the most important issues was the black body radiation. That was the perfect tool to calibrate temperature. But then essentially when physicists study the black body radiation, black body is essentially imagine an abstract sort of sphere, if you wish, that is completely dark, and there's light inside, and there's one hole somewhere on the sphere, and through that hole, light is emitted. And the frequency of the light depends on temperature. The intensity depends on temperature for a given frequency. Anyway, so people were studying this, they estimated what is essentially this picture of the intensity that depends on temperature and frequency, and essentially it was impossible to solve the problem. And it is when the physicists faced the problem of ultraviolet catastrophe. It seemed like if you go with the wavelength or to zero or frequencies to infinity, then essentially everything explodes in a sense of intensity of the radiation for a given temperature. So Planck was studying this problem, and essentially in order to sort it out, he essentially introduced as a very abstract concept a quantum of energy. He thought, okay, the energy is not emitted from this black body continuously, but essentially in kind of packages of energy. And that solved the black body radiation problem and ultraviolet catastrophe. So that was a completely abstract, and it was as he wrote later on, it was act of desperation to figure out how to solve the problem ultraviolet catastrophe. So h bar, that is the Planck constant, was introduced. Professor Janssen gave the numerical value. It's very small. It's measured it's as an action, physically as an action, and that was introduced. 5 years later on, young Albert Einstein, in his Annus Mirabilis, tried to solve another very pressing problem. People were puzzled how it is possible that you irradiate a solid with light, and essentially you expect some electrons to be released from the solid, or in the solid. However, these electrons were released not depending on the intensity of light, but on the frequency, which was really puzzling. And the reason, and many of you know that, is the fact that there have to be quantum jumps between different orbits in atoms in order to the electron to be released, and for that you need a very specific frequency. So now we are in the situation where the radiation is, when the light is irradiated in quanta and also absorbed in quanta. So that was 1905. Now, here, I mean, there was a lot of quantum physics, Rutherford and everybody else, but essentially these are the essential issues that led to the year 1925, 1926, when 3 young physicists formulated the foundations of non-relativistic quantum mechanics as we know it today. So in 1925, when Heisenberg wrote his matrix mechanics, then in 26, Erwin Schrödinger wave mechanics, and in 26-27, Paul Dirac unified the 2 kind of mathematical formulations that show that they're identical. So just a comment as a footnote, Heisenberg, at the time he published his paper, was 24 years old. It's amazing. And the same for Paul Dirac. It was his thesis, which is called quantum mechanics. So these guys were 24 years old when they essentially revolutionized the whole physics and turned it completely around. Now, 2 years later on, there was this famous Solvay conference, and as you can see, if you look at the picture of 1911, these 3 guys are missing. However, here you have them all, among Schrödinger, Heisenberg, it's Paul Dirac and also Wolfgang Pauli. So it's amazing. This is the conference where the quantum mechanics was really kind of accepted as a really full-fledged theory. Now, what are the basic what is the essence of quantum theory? So we have the energy quantized. Second, there is an uncertainty principle. You cannot measure simultaneously, and you remember that from school, you cannot measure simultaneously the position and velocity of a particle simultaneously. It's impossible. There is always some fundamental uncertainty in the measurement. We can call it quantum noise. So even at the level of vacuum, there's a noise, quantum noise. And there's the third kind of aspect that was already mentioned is wave-particle duality. Depending what type of measurement you perform on your system, it can behave as a wave or it can behave as a particle. If you measure interference, you will say that it's a wave. If you are detecting the single events, then you say it's a particle. Now, what are the quantum effects? You probably know all of them. So discrete spectral lines, it is because of the discrete nature of atomic orbits. Then you have that matter can behave as a wave, so electrons can behave as waves. Another effect is quantum tunneling. Unlike in classical physics, when you have a barrier which cannot be penetrated by a classical particle. Quantum particle with some probability can penetrate. Then you have the interference, various types of interference effects, and you can use them for very nice applications. Now, I will talk in much more detail about quantum randomness. This nature we are living in is fundamentally random, stochastic. Whatever we do, we cannot predict with certainty. And finally, I will talk quantum entanglement. So these are the basic quantum effects on which all the quantum physics essentially is based. Now, usefulness of useless, yet another historical story. In 1850, William Gladstone, who was the Chancellor of Exchequer those days, visited the lab of Michael Faraday. And he asked, what is the practical value of electricity? It was 175 years ago. And the answer was, which is the famous answer of Michael Faraday, I don't know, sir, but I'm sure one day you may tax it. So essentially, that is exactly, we do not know with some kind of new things physicists find what they are good for, but as Michael Faraday said, you will be able to use it for taxing purposes. Now, certainly it's a problem. The quantum, essentially, that is the result of quantum, which all we are worried about, and essentially one of the reasons your organization exists is really to prevent this type of events. So, but from a positive point of view, what has quantum mechanics ever done for us? You asked, it's a very legitimate question. Now, in fact, if I look on my mobile phone, it's packed with quantum physics. Essentially, any technology you have here is rooted in quantum physics. So it's semiconductors, transistors, microchips, LED and OLEDs, lasers, solar cells. It's all quantum physics. Electron microscopes, wave properties of electrons, PET and SPECT scanners. I mean, you have the processes like positron annihilation and gamma photon emission. Magnetic resonance imaging. It's again a quantum effect that helps us to image. Communication navigation. Many people now, during the panel, mentioned fibers. What do you send through the fibers? Laser of light. Laser light with the quantum coherence is a quantum system. Atomic clocks. Professor Janssen mentioned optical quantum and atomic clocks, and there are some quantum clocks as well, which I will mention briefly at the end of my talk. So, just to convince you that how important it is, I just made a short survey of how many Nobel Prizes were given for quantum physics and early foundations. I'm not going to read those names. They're famous and you all know all of them. Then developments of quantum mechanics, our three heroes here. Quantum matter and materials, whole spectrum of Nobel Prizes. Quantum optics. Again, the last one in quantum optics was given to Roy Glauber and John Hall and Theodore Hansch. So it's amazing. It's really amazing. And there's more to come, but there's a serious problem. That essentially everybody was quietly walking around, and it was Einstein who first essentially was worried by the problem. It's called EPR paradox, Einstein-Podolsky-Rosen. Einstein figured out that quantum mechanics as formulated violate the basic principle of classical physics, local realism. That is, properties of systems, physical systems, are defined locally. They do depend only what's happening in a close proximity of the particle of the system. And they really exist, whether me observing or not observing. I cannot affect by observation the state of physical system. And Einstein has shown that there exists within quantum physics, quantum mechanics, type of correlations that violate this locality principle. And that was like complete shock. And people were sort of uncomfortable with the situation. However, quantum mechanics worked so well in so many other contexts that essentially we live with that problem unsolved, and essentially everybody was kind of quiet about it. People like Einstein himself suggested maybe there are some hidden variables we are not able to detect, or we do not know them, so there's some kind of knowledge we do not have about a physical system, and therefore quantum mechanics behaves so strange. In order to illuminate this, I will just repeat in a little bit different sense what are the three pillars of quantum physics. It's quantum superposition principle, it's quantum measurement, it's very tricky stuff, and quantum correlations, quantum entanglement. Now, in order to illustrate it, I will use the concept of two-level system. Like in classical physics, we have a classical bit. It's a 0 and 1. It's a unit of information, 0 and 1. And in classical physics, the system is either here or here, 0 or 1. You might not know, so you say with some probability it's 0 or 1. But it's still, in reality, it's in a very definite state. So this classical bit. In quantum world, the situation is different. Quantum bit, qubit, can be simultaneously 0 and 1. Even though it seems like almost nothing, but it's a radical deviation from classical physics. Something can be simultaneously north and south, dead and alive. And it is exactly where the double-slit experiment will help us to understand the essence. Because, as Richard Feynman said, the double-slit experiment is in the heart of quantum mechanics. In reality, it contains the only mystery of quantum mechanics. Now, what is the double-slit experiment? Imagine you have two screens. In one screen, you have two narrow slits. The other is a projection screen, projection panel. Now it is important what I'm going to say. One by one, you are sending electrons through these two slits. One by one. You do not control which of the slits the electron goes, but what happens at the other side of the slit, on the screen, the electron is absorbed by the detector at a very specific point, a very specific pixel. So it's click, then another electron comes, goes through the two slits, and is absorbed in different point, and different point, and different point. So essentially, as you have the stream of electrons, each electron flies through the double slits, and then is absorbed on the screen behind. If you perform many, many measurements of this type, at the end of the day, what you see is this interference pattern. So essentially, it seems like it's very similar to what is in classical physics for wave physics. So it's not one big peak, broad peak, but essentially it's line by line, line by line. It's quantum interference. So, but I stress, it's not that electron goes through one slit or the other. Electron goes simultaneously through both slits, but is detected at one point. In order to illustrate and now to proceed with concepts, so essentially imagine another two-level systems. And there are many two-level systems, like we have double slit, but you can have many other, like spin 1/2 particle is purely quantum, but essentially it can rotate clockwise or anti-clockwise. Now, it is what you perfectly understand what it means, clockwise, anti-clockwise. But what happens if simultaneously is clockwise and anti-clockwise? It's totally different situation. And the point is that you can superpose these two kind of classical situations, like logical 1 and logical 0. You can superpose. They are simultaneously rotating one another direction. And here is the point. If you try to describe quantum mechanically, what is the state of that sort of spinning system that is spinning simultaneously to the left and to the right, then you can't describe it only by two values, north and south, but essentially it can take any arbitrary sort of superposition. And that is described by a state space, which is a Bloch sphere or Poincaré sphere. So essentially, the quantum state, that is superposition of two classical states, is represented by a point on a sphere. Now, you know how many bits you need to specify the coordinates of a point on a sphere? I mean, you know that. It's essentially, it's infinitely many number of bits, because this is a real number. There are two real numbers. So essentially, to specify a state of a single qubit, you need infinitely many classical bits to determine it. And this type of superposition essentially is the whole potential for quantum computation. You can encode that much, a lot of information in a single qubit, and then you can process it somehow. Now, but if this is that way, it's very simple. The story is much more complex because of quantum measurements. And the quantum measurements is something that is really extremely tricky in physics. We do not know exactly what it means. We know the data, but fundamentally, it's really not known exactly. But there are some principles you can be sure about. So, outcome of a measurement performed on a quantum system can be only predicted statistically. There's uncertainty in this universe, fundamental uncertainty. So the quantum world, at the level of classical description, is random. Now, it's even more important. By performing a measurement on a single qubit, we obtain result either 0 or 1, or any other like a projection, but just one bit of information. But we cannot tell exactly which bit it is. So information gain, this one bit of information, destroys the quantum information encoded in a qubit. So by performing a qubit, you just receive one bit of information and you destroy all the information in the quantum system, which, by the way, is the basis for quantum cryptography. So there's an information gain versus disturbance. More I gain information from quantum system, more I disturb it. And okay, there are some extreme views here. Properties that were determined by quantum measurements didn't exist before the measurement was performed, which is really a very extreme approach to quantum measurements. So before we observe the world, and after we observe it, there are two different states of the world. So quantum measurements is very strange. Now, I told you about the wave character of electrons, double slit. But because you are clever, you say, okay, I have to figure out essentially. I can figure out which slit the electron goes through. It's very easy. I just shine the two slits with different frequencies, and depending on reflected frequency of the light, I will say the electron went through the one or the other slit. However, when you do this, you receive information about which slit the electron goes, but you destroy interference pattern. Because you gain some information, and therefore you destroy the information, this quantum information. By the way, it's really funny. In English, you say quantum information processing with no problem. In any other, in Slavic languages, you cannot say that. It's either quantum information processing or quantum information processing. And there are two different concepts, as you can understand. Either you quantumly process information, or you process quantum information. Anyway, that was just a footnote. Now, and here is the quantum entanglement, which is the most bizarre property of quantum systems. The two objects that were created simultaneously and because of some conservation laws are correlated in a very unusual way. In a sense, each of the objects individually has no specific state. But once you perform a measurement on one of the objects, the other instantly is 100% correlated with the result of the measurement. So that's quantum entanglement. People were sort of uncertain what to do with this and how to deal with the problem Einstein in 1935 formulated. And then it was only 1964 when John Bell from CERN formulated mathematical inequalities such that if the inequalities are fulfilled, then the theory is sort of, you can say, it's classical. If they are violated, then you are certain that even if there exists a local hidden theory, it has to be non-local. So if they are violated, the world is quantum mechanical, fundamentally, irrespective of your other theories. And then, several years later on, Alan Aspect performed a measurement of these Bell inequalities. And he has demonstrated that they are violated. So from this point, we all know that universe is quantum, that the nature around us is purely quantum. And if to paraphrase Einstein, classical reality is just an illusion. It's all quantum. Now, that was quantum mechanics in 10 minutes. But if you think you understand quantum mechanics, you don't understand quantum mechanics. That's Richard Feynman saying. Now, second quantum revolution. All the revolutions start with a very simple question or statement. And the statement at the beginning of this revolution was by Erwin Schrödinger in 1952. In the first place, it is fair to state that we are not experimenting with single particles any more than we can raise ichthyosauria in the zoo. We are scrutinizing records of events long after they have happened. Therefore, I said, you observe what's happening on the screen. So it's first click, and then you collect many, many clicks, and you see the interference pattern. And Schrödinger was certain it's impossible to manipulate with individual quantum systems in real time, 1952. And classics of physics, Niels Bohr and Wolfgang Pauli, we are all agreed that your theory is crazy, that is, if you think that you can manipulate individual quantum systems. The questions that divides us, whether it's crazy enough to have a chance of being correct. And yes, that idea of manipulation of individual quantum system turned out to be correct. And 60 years later on, a Nobel Prize was given to Serge Haroche and David Weiland for exactly manipulation of individual quantum systems. So imagine that you have a trapped ion, or you have a photon in a cavity, single photon in a cavity. The cavity is high Q cavity, so the photon lives very long time there. And you can manipulate its state. You can manipulate, you can create a Fock state, you can create coherent superposition of Schrödinger of coherent state, and so on and so forth. So it's really amazing that, and this is exactly what second quantum revolution brings, manipulation with individual quantum systems. So, and here starts the absolutely fascinating story. The same Richard Feynman in 1981, in a discussion with Charlie Bennett from IBM, they realized that essentially quantum physics, to simulate quantum physics, you need something more than classical computers. And Richard Feynman formulated it the way that if you want to make a simulation of nature, you'd better make it quantum mechanical. And by golly, it's a wonderful problem. It's a wonderful problem because it is really very difficult, and this is where we have to concentrate. The same year, there was a conference at the MIT, and in '83, the first BB84 protocol was formulated for quantum cryptography based on individual quantum systems. Then in '85, universality, like you have a Turing universality here it was David Deutsch. In '94, it was the first algorithm that essentially have demonstrated that we can perform on quantum computers calculations much faster than classical computers, and then everything evolved. Experimental quantum teleportation was demonstrated by Anton Zeilinger, who is from Vienna, who essentially has shown that quantum entanglement can be used for teleportation of unknown quantum states. In 2016, for quantum communication, it was the first Chinese satellite that was launched, and there was a quantum link between China and Austria. Amazing things happens. And certainly 2019, it was the first time that John Martinez from Google have demonstrated that the quantum computer can solve the problem that classically is untractable in real time. So it is where it happens. And there have been, again, another 4 Nobel Prizes for this second quantum revolution results. And as Bill Phillips put it, quantum technologies is a radical departure in information technologies, more fundamentally different from current technology than the digital computer is from the abacus. Now, you can use quantum entanglement for amazing things. Professor Hansen said about the metrology, but essentially you have quantum memories, quantum repeaters, amazing stuff. You can use non-locality really to fundamentally use it or exploit for different type of applications. There have been many models of quantum computers being, it was mentioned, optical lattices, superconducting qubits, the optical qubits in optical cavities, NV centers. So many technologies have been developed. And then essentially, I'm going to skip this part because Professor Janssen demonstrated a lot about the potential quantum technologies in seismology. But essentially, what I have here, I just will briefly mention quantum gravimetry, quantum gyroscopes and accelerometers, quantum magnetometers, quantum clock, quantum communication, quantum computers. From the bottom to the up. Quantum computers, you definitely, if you have a lot of data, then essentially your classical computers will not be able to process it enough. In the morning session, we have the AI. I'm really convinced that proper general AI stuff will be run on quantum computers. It is where essentially where it will happen. Hopefully we will have quantum memories, and if we have them, then it will be a completely different story. Quantum communication, whatever the data you have, you'd like to securely transfer it from one place to another. Quantum communication offers you a very good solution. By the way, you said that it's in the early stages, but you can buy it's rather even cheap to buy a quantum communication link. It's really, the problem is you need dark fiber, and there are these two protocols. It's either BB84 or Ke01, but essentially one is based on individual photons, the other way is based on entangled states. But you can use it. And as some people say, in China, it's essentially used everywhere. It's still more costly than classical or post-quantum cryptography based on mathematical complexity. But for sure, if this is becoming cheaper, that will be the technology of the day. Now, quantum clocks, even though we have single ion optical clocks with a precision of 10 to minus 18, minus 19, but they are intrinsically quantum clocks. They are even order of magnitude better. So imagine the precision of the timekeeping. Imagine the GPS precision with such clocks. Okay, so quantum communication is really either based on single particle, single photon transfer or entanglement. And here is the comment that even in 2005, it was, the first demonstrations was in '84, I believe, at the IBM, but it was on a table via the fiber. It was Charlie Bennett and Gilles Brassard who made the experiment. But essentially in 2005, we had the first ever cross-border quantum key distribution protocol realized between Austria and Slovakia. And now essentially we have running link between Vienna, St. Pölten, and Bratislava. And presently we are building, as a part of huge European initiative, it's called EuroQCI, Quantum Communication Infrastructure. And we believe in seismology, it can be used rather heavily. Okay, with this probably I'll finish, is the famous quote from Sun Tzu, The Art of War. The Sun Tzu said, the art of quantum is the most important art for the state. Thank you.
Thank you very much, Professor Buzek. Amir, behind you. So we have time for one or two questions, which I know that there is a coffee break coming, but I'm thinking maybe there is a question in the audience, otherwise I will have one online. So we will take, I guess, one or two questions. So the question that we have received online for you is, thank you for showing us how quantum effects are part of our daily lives and in devices that we know from our daily lives. When do you think we may see quantum computers help us solve large computational problems unsolvable today? Is it years away? Is it decades away?
It's always 20 years away, because in 20 years, those who say that will retire. The first ever European meeting was in 1998 in Helsinki on quantum technologies. And everybody attending, these were the people who have Nobel Prizes now, were saying in 20 years' time. Okay, I believe that after 2019 result of John Martini's, and the fact that we have the Chinese quantum computer, we have IBM, we have VTT in Helsinki. So it's really behind the corner. It's difficult to say. It's difficult to say, to predict exactly, the question is more important question, which type of problem will be solved? And there are really difficult, complex problems like design of big molecules for pharmaceutical industry, for instance. So we do not expect to have calculations as we know it, but essentially what is expected to have different type of simulations, optimization problems. This will be the first task of quantum computer, and essentially it can be next year.
Thank you very much. So I think you have given us a lot of things to think about, and I know that we have a lot of material, and we will discuss with you if we can make it available to the audience, because I know you have to go fast toward the end. But we appreciate that you were here. So I'm just looking if there is anyone that wants to ask a question in the audience. I think we are.
They're all tired.
They're thinking a lot, I'm sure. They are thinking about what did they learn and what they want to do. So thank you very much for being here for the Quantum Day. Thank you very much for the talk.
It was my pleasure. Thank you.
It was our pleasure to have you. Thank you also to Professor Jensen for being here. I don't want to stand in your way to the coffee, so I think the coffee break is starting now. And thank you again.
Thank you.